So far, we've looked at two programming paradigms. We've looked at functional programming in ML, and we've looked at imperative programming in BASIC. Today, we will look at Prolog, which is quite interesting because it's based on a different basic principle. In all the things we've written before, we have this idea of a state that's transformed step by step as the program evaluates. Prolog works differently. In Prolog, you write in a declarative style, which means that you specify what you want, but don't tell the system how exactly. Functional programming is also declarative, but even in functional programming, you sort of say step by step what needs to happen. And that's not how Prolog programs run. Prolog programs are written as a set of facts and rules. Facts describe some basic things, basic facts about the world, and rules are a bit like logic inference rules, how you can derive more information from the facts you have already. The evaluation in Prolog is then done by some clever inference engine that uses the rules to deduce new information from the facts it has. Prolog and similar system, including Datalog, are available today. It's a programming environment that you can use. There's various interesting implementations of these things, and some of them are used in practice for various examples. We will look at some of them later on. But this mechanism is also used as a basis for some other system. So if you have something where you need to derive information from basic facts, those kinds of systems are actually a nice fit for that. Interestingly, Prolog and logic programming in general has origins in the world of AI, not the kind of modern AI that we use today, but AI that was very much based on symbolic representation of knowledge about the world. And it was also based on trying to model natural language. So those are the origins of AI, and it's an area where it may still be useful. In the previous lab, we've looked at type inference. So Prolog works in many ways surprisingly similarly to type inference. In type inference, what we were doing is that we were analyzing programs. So we used some logic inference for program analysis. And the way it worked is that we generated a set of constraints. Then we had some unification to resolve the constraints. And we used type inference to assign types to our program. And the basic logic behind it was built around unification and substitution. So those are the things you've written already. In logic programming, we are using these same mechanisms of unification and substitution, but we are using them for program evaluation. So when you run a program, it will be actually doing this unification and so on. The constraints that you write, the things that your engine will need to resolve, they will be handwritten. That's your source code. The program itself is written as sort of constraints. In type inference, our unification worked on this structure that represents types. In logic programming, we will be unifying structures that represent terms, a bit like in logic. And instead of inferring type assignment, instead of inferring the types, we are inferring variable assignment. So we run this inference engine to calculate the values for the various variables that exist in our program. Looking at the history, one of the first uses of logic programming systems was natural language processing in the 60s and 80s and 70s, and systems like Planner were trying to let the user manipulate objects or communicate with the system in a natural language using sentences like find a block which is taller than the one you are holding and put it into the box. So here you can imagine what the knowledge representation was like. They must have had predicates for sizes of boxes, for what is inside what, and the system would then interpret the sentence and try to find a solution of steps through which it can change the state of the environment. And this was predecessor to logic programming. In the 1970s, Alan Kollmeier in Marseille started developing what would become Prolog. Again, looking at natural language processing as one of the applications, but another area where this was used very early on was automatic theorem proving. So trying to get the program to automatically derive proofs for mathematical theorems, inferring all the possible steps. An interesting bit of history is that in the 1980s, partly in response to the US developing a lot of AI systems around Lisp, in Japan there was a 10-year initiative to develop fifth generation systems, and this was based on Prolog. So this was a massive government investment into developing Prolog-based AI systems, and it had some interesting results. It contributed to the development of concurrent programming in Prolog, better knowledge processing, but it definitely didn't have as much an effect as the government was envisioning. Today, Prolog itself and a sort of variant on Prolog called Datalog, there are things that can be used in some specialized domains and in practice, but there are also foundations for other systems, and we've seen that type inference is based on the very same principles. So I'm going to do the typical Prolog hello world, which is querying a family tree, and we're going to have a little representation of a part of the British royal family, and we'll do some inference. This is a good primitive example because you have some facts, who's a male, who's a female, who's a parent of whom, and then you can define derived rule. For example, a grandparent is a parent of a parent, and father is a parent who's a male. The other demo that I will show you briefly is list processing. And in Prolog, lists are represented using the same data structures you've seen in functional programming. So you have a list, which has a cons, that's the first, the head element. You can have a list which is either a cons or nil, and cons means there is a head element, the first element that's followed by some other list. So linked list with the first thing and then some more, or it can be empty. And this works very well with pattern matching, and that's indeed how we are going to process lists in Prolog. The interesting things that I will show you is that in Prolog, because it works by deriving facts, many functions actually become multi-purpose. So if you write the function, it can be used with different parameters as inputs and outputs. So for my first demo, I have a file that defines some people in the British royal family. There's some males, some females. So those are my British family people. Then I have a predicate called parent, which defines that the first argument, the first person here, is the parent of the second person here. So I'm saying that Elizabeth is the parent of Charles and Philip is the parent of Charles. And then we are defining that Diana and Charles are parents of William and Harry. And I just picked a couple of people here. So I'm saying that parent, that William is the parent of George. So that will be enough for me. And then I have this derived predicate that says father XY, so someone is a father of someone else, if the person X is the parent of Y and the person X is also male. And similarly, I can define mother. Now, what I've got here is a Visual Studio Code plugin for Prolog. So I can say load, and this will now load the file that I defined here into this interactive terminal. And now I can say, well, let's see who are children of Diana. So what I'm doing here is I'm with lowercase, you're specifying atoms. That's something that you define in your world, and the uppercase letter means a variable. And so here I'm saying, well, find me assignments for the variable x such that the x is a child of Diana, or Diana is a parent of x. And then I type dot, and if I say enter, then it gives me the first assignment, which is William, but I can then continue ask for more values, and I get Harry. Now, if I wanted to ask who's the father of William, then I say father x William, and again it will find me the assignments, and there's just one, that's Charles. Now, if I want to define grandparents, then I can say grandparent, and now I want to define that x is a grandparent of y. So how do we do this? Well, there needs to be someone who's, well, x needs to be a parent of someone, but we don't know who that is. That could be anyone. So we use a new variable here. And then also this new person has to be parent of y. So I'm sort of introducing a new link in between, in the middle here. I can define grandfather. This you could define in two ways. We can say grandparent x and y and male x. So this is the same style as we use here, but you could also say grandfather is a father of someone, and then that person is a parent of someone. Okay, so let's try this. I'm going to reload my definitions, and now I can say I can look at who are all the grandparents of George in my data set. Okay, so that would be Diana, Charles, or I can, for example, switch this around and see who are the grandchildren of Elizabeth. So that's William and Harry. This is interesting because when we are defining these predicates, we are not saying what's an input argument, input variable, or input parameter, what's an output parameter. That it can be used in both ways. The best way to illustrate what this lets you do is to look at lists. So here I'm going to show you how you can define some functions for working with lists in Prolog, and I have some helpers above that I will need later on. But let's start by defining the function to append to lists. So what I want to define is a function called append that takes that has three parameters. It has x and y. They're the lists that we want to append, and then it has a parameter z that represents the list that we get as a result if we append x and y. So that's the function that we want to define, and I said before that lists in Prolog are represented using linked lists. And so what do we do here? Well, if the first list, if this is empty, and then we have some x, then the result is x. So now we define the first fact, which is that if you're appending x after an empty list, the result is x. So this was easy. And now the more interesting case is if we have a non-empty list as an x. So here I have a non-empty list which starts with x and then it's followed by some xs. and then I have some other list y. And then I will need to put something here, but I'll have to think more about this. So what do we do? Well, you can expect that we need to use recursion here. So if I say append again, and I recursively append x's and y, and this gives me some z, then z is the concatenation of x's and y, and the overall result that I need to put here is going to be x followed by z. So I'm going to use, again, this construct, cons syntax, and I need to put dot at the end, and now I'm able to load the file, and we can see if it works. So if we append 1, 2, 3, and 4, 5, 6, and get the result as x, then this did work, and we get a list 1, 2, 3, 4, 5, 6. As I was saying, an interesting thing about Prolog is that we can use the functions in multiple ways, or the predicates. So if I say something like this, I'm basically asking Prolog to derive x and y such that if I append y after x, the result will be 1, 2, 3, 4, 5, 6. And if I do this, I had a typo, so Prolog helpfully asks me if I want to correct my typo, and I can see that one possible assignment for x and y is x is empty, y is the whole list. This is true, this is one possibility. But we can ask for more. We can ask for another solution to the task, and that's a list with 1, a list with 2, 3, 4, 5, and so on. And as you're doing this, Prolog actually generates all possible assignments until it reaches the end, it finishes the search, and then it says false. So this is a very interesting property of code that's written in Prolog. Now I want to show you one other interesting thing, and this is, well, let's say that we want to sum the numbers in a list. So we want some predicate called sum, which takes a list and gives us a number. Well, if the list is empty, then the sum is 0, so this is an easy case. And what do we do for the other case? If the list is non-empty, well then, what we need to do is that we need to sum recursively xs, and this gives us some n, and then we need to return some n and 1, let's say, which is going to be n plus x. And the result will be n1. So I've intentionally written this in the way that you would probably write this if you didn't know Prolog, but there's a trick here. So what do we get if we say sum 1, 2, 3, 4, 5 and n? Prolog tells us that n is 0 plus 5 plus 4 plus 3 plus 2 plus 1. So that's true, but it's not the number that we want. So when you have plus in Prolog, it works just like other predicates. It's really just a predicate with some arguments, and Prolog constructs the assignment to n in terms of the predicates that it has. So the important thing that does not happen here is it doesn't actually evaluate the plus, and you can get Prolog to do that if instead of using equals, you use is. So there's a special extension in Prolog for forcing the execution, and if we now reload the file and run sum, then we do actually get 15. But of course, this also means that if I tried to say sum L 15, Prolog cannot solve this because it doesn't know how to unplus numbers. So this is the hello world of Prolog, and as an example of what you can do with Prolog, and as an example of something that we can actually write in our TinyProlog later on, I want to give you an example of a code that calculates magic squares. And we're going to do this in the most naive way. So a magic square is this 3 by 3 grid of numbers from 1 to 9, where if you sum the rows or the columns or the diagonals in any way, you always get 15. We are going to solve this in a most basic way, where we just say we take all permutations and test whether it's a magic square. That's very inefficient. It generates a lot of bad solutions that it generates and then rejects. And there's many better approaches. You could try starting with one row where the sum is right, and then adding by sort of using the numbers that you haven't used already, for example. And that's much better. You can try that. But the naive solution will be good enough for us, and we can actually try to run this in our TinyProlog. So how do we do this? I'm going to define a function called magic, and this will take a list, or it will have a list as an argument, and I will make this a nested list so that we can see that the 3 rows. So I have a list of 3 elements, which are each a list of 3 numbers. And I am basically not defining an algorithm to construct a magic square. I am just defining a predicate that says this thing is a magic square. So when is this list of A's, B's, and C's, when is it a magic square? Well, the numbers have to be some sort of permutation of 1 to 9. So that's where I can use my helper n 1 to 9, because I can say n is my numbers, and then there's a built-in primitive called permutation, where I can say n is a permutation of A's, B's, C's. And actually I can, just to see what happens, I can run this already, and if I say magic L, right now this will generate all possible permutations of 1 to 9. So it's not generating magic squares, it's just iterating through all the permutations. So now we need to add the extra conditions that the rows, columns, and diagonals have to be all 15. I'm going to start with the diagonal, which is, the first one will be A1 plus B2 plus C3. And I want to say that this needs to be 15. And to force the computation, I'm going to say 15 is, and then the sum. And I'm going to do this in the most naive way, just by adding one line for every condition. You could do something more clever, like construct some list of things that have to sum to 15 and so on, but this will be good enough for us now. So we have a condition for the 2 diagonals, then we have 3 conditions for the rows, and then we have 3 conditions for the 3 columns. And if I load my code again and ask for magic squares, then, well, you'd have to verify that this is actually true, but this is 15, there's 15, there's 15, so it probably is true, and you can ask for more magic squares, and Prolog in this case can actually generate a complete list of all possible magic squares.